1.7 is about operations on functions or combinations of functions. One thing that we need to consider when we combine more than one function is that the resulting function has to have the same domain restrictions that the original functions had, plus any that happen when they get put together. Okay, so what I mean by that is we need to find, so let's say we are dividing two functions, f over g. Okay, we need to figure out what is the domain of f, what is the domain of g, and if there's anything that cannot be part of f or g, we need to take those out of the domain of the quotient, okay, f over g, like the new function, all right? And so really what we do here is we start with all real numbers, and then we look for what can't work. Things that can't work are things that cause us to divide by zero. So if we have a fraction and we get a zero in our denominator, we know that that can't be in the domain. And then also, if we have a square root or a fourth root or a sixth root, anything with an even root, I think here, yeah, right here, this should be in, oh no, that's just the word and, in an even root, okay, so like a square root or a fourth root, etc. We can't have negatives under there. If it's a cube root, that's totally fine. We can have the cube root of a negative number, but we can't do the square root or the fourth root or the sixth root or the 12th root of negatives. So we take those, anything that would make those negative, the radicand, the part under the radical negative, we take those out of the domain. Okay, so first, just some practice with the domain. This is just a plain polynomial. There's no domain restrictions on a polynomial. So the domain is all real numbers, or negative infinity to positive infinity. For this one, we have a fraction, and I need to know what makes my denominator equal to 0, because I can't have that in my domain. So I'm going to start by just solving that for 0. So x squared minus 2x minus 3. I'm going to set this equal to 0. And this is factorable, x minus 3 times x plus 1 equals 0. So x equals 3 and negative 1. Now remember, these are the values that x cannot be, because it gives us a 0 on the bottom of the fraction. So we're going to say negative infinity to negative 1 open, and negative 1 to 3 open on both ends, and 3 to infinity. Or if you just want to write all real numbers except x cannot equal negative 1 or 3, that would be fine as well. I don't know if like Pearson cares about interval notation or not. I'm fine with interval notation, which would be this, or I'm fine with you just saying what the restriction is, as long as you start with all real numbers, okay, which is that script R. Okay, right here, I can't have a negative under the square root, so I'm going to start by solving 3x plus 12, and I'm going to set this equal to 0. You don't have to write the word set over the top of the equal sign. I like to do it because it shows that I'm being intentional about saying I want to know where this expression is equal to 0, not that it's just an automatic assumption that any expression is always equal to 0, okay? All right, so when I solve this, I get 3x equals negative 12, and then I divide by 3, and I get x equals negative 4. So x, now, it's not that x can't be negative 4, because negative 4 would give us the square root of 0, and the square root of 0 is 0, and that's totally fine. What we can't have, though, is we can't have any number that is less than this, okay? So really, backing up to the beginning, if you want to start by writing 3x plus 12 is, now, you decide how you want to do it. If you want to say, I'm looking for the exceptions, this can't be less than 0, and then you could solve that. Or you can say, I'm going to look for what x can be, and I'm going to say 3x plus 12 can be greater than or equal to 0, okay? Either way, we're going to get x is greater than or equal to negative 4. You could leave it like this in inequality notation, or as an interval, you could say from negative 4 inclusive, because that gives us a 0, to infinity. Okay, so that's our domain there. And then for this one, again, we don't want anything under the radical to be equal to, or sorry, we don't want it to be negative. In this case, we also don't want it to be 0, because the square root of 0 is 0, and that would be division by 0. So that would actually give us a problem with this first condition, not the second. So I'm going to do, for this one, I'm going to say, what can x be? And I'm going to say any value where 14 minus 2x is greater than 0, but I'm not going to have the or equal to part. okay? So to solve this, I'm going to subtract 14, negative 2x is greater than negative 14, and then I'm going to divide by negative 2, so I get x is, if you remember from Algebra 1 topics, when we divide by a negative, we change the direction of the sign, so x is less than negative 7. So this is what x can be, or again in interval notation, negative infinity to negative 7, and here the end has to be open. Okay, if you have any questions about domains or how I did any of those, let me know. Let's go ahead and look at some operations on the functions. Okay, so all of that was just kind of once you get your new function, what is its domain? So it is something we need to consider. Okay, all right, so for this, actually I'm gonna cheat here and move that down and move this part up. There we go. Okay. Close enough. Let me get rid of that line. So if we have the quantity f plus g of x, then that means we take f of x and g of x and we add those together. Adding those together means combining any like terms and then having a new resulting function that's a new function, okay? And then same thing for the difference. So this would be f of x minus g of x, okay? A product, you might see a little dot on the inside there, or maybe not, but that means we are multiplying f of x times g of x, and then the quotient would be the same as f of x divided by g of x. Now, here we do need to add that, that g of x cannot equal 0, okay? Because now we have a fraction, and we need to make sure that in the resulting quotient, the denominator is not 0, okay? So in addition to the original domain restrictions that need to come out, we also need to check to make sure our denominator is not 0. All right, so let's do a few examples of this. Okay. Oh, nope, never mind. These are, sorry, we're not quite to the combinations yet. Here we are still looking for domain restrictions, okay? But these are functions that are made up of more than one piece. So if I have a function here and a function here, I need to figure out, and I'm subtracting those, I need to figure out the domain of my resulting function. Anything that makes either denominator 0 is going to be a problem. So x cannot be negative 8 because of this fraction. X cannot be 10 because of this fraction. So my domain is, and I can say all real numbers such that x does not equal negative 8 or 10. Or in interval notation, I could say negative infinity to negative 8 and negative 8. Oop, that's not an 8. Negative 8 to 10 and 10 to infinity. Either one is fine. This one's probably easier. Okay, for this one, now I need to know where we have x values that make both of these expressions non-negative, okay? So if x minus 3 has to be greater than or equal to 0, that means x is greater than or equal to 3. And here, x plus 4 has to be greater than or equal to 0, so x has to be greater than or equal to negative 4. Now, think about a number line. Greater than or equal to negative 4 would be all of these values. Greater than or equal to 3 would be all of these values. So we take the most restriction that there is, and we're going to stick with positive 3 to infinity. So this is our domain, or we could write it as positive 3 to infinity, like that in interval notation. So the reason that we're picking this one is because it restricts a little bit more. If I pick any number in between negative 4 and 3, even though this one will be fine, this will give me a negative under the radical, and I can't have that. Okay, over here, looking at each one, there's no problems with the x minus 5, but here I can't have a square root of any negative numbers, so x has to be greater than or equal to 0, which in interval notation is 0 to infinity. Okay, and then lastly, this one over here, in my original function, the way that it's written, I can't have a 0 in my denominator, so 4 over x minus 1 cannot be equal to 0. Now, I'm going to solve it as equal to 0, and then that will just be my function or my domain exception. Okay, so I'm going to, now you can write this all out. So we can add 1 and write 4 over x equals 1, and then multiply by x, so 4 equals x, or you really could just say something minus 1 equals 0. What makes this fraction equal to 1? Well, if the denominator is 4. So either way, our domain is all real numbers except 4, okay? Because that would give us a 0 in our denominator, or we could say negative infinity to 4, open, and open 4 to infinity. Okay, now let's put some of the functions together. So we're starting with f of x is x minus 5, g of x is x squared plus 1, and we are applying these operations, okay? So first of all, f plus g of x is going to be f, which is x minus 5, plus g, which is x squared minus 1, and then I do have some like terms that I can combine, so I'm going to write this as x squared plus x minus 6, because I'm combining those two, and then we stop there. Domain restrictions would be none because the domain of both of these is all real numbers. So we don't need to worry about that here. Okay, f minus g of x. So now I'm going to do that is equal to x minus 5 minus the quantity x squared minus 1. And I know you've heard me say this on more than one occasion, but you have to use parentheses because the negative has to get distributed. Please use parentheses carefully, okay? I need to put my entire g quantity in parentheses. So this is negative x squared plus x, and now negative 5 minus negative 1 is negative 4. I don't care about the order. Like if you write this x minus 4 minus x squared, that's no problem, okay? Once again, no domain restrictions, so all real numbers. Okay, here we are multiplying f times g, so again, using parentheses appropriately, it's the quantity x minus 5 times the quantity x squared minus 1. Okay, I'm going to multiply those together and get x cubed minus 5x squared minus x plus 5. Okay, if you have questions on multiplying or factoring polynomials, please ask questions. They are not going away for the entire semester. We have to be able to do that. I can help you. You just need to let me know, okay? All right, and then lastly, and again, no domain restrictions. And then for D, we're doing f divided by g. So this is equal to f of x, which is x minus 5, over g of x, which is x squared minus 1. Now, I cannot reduce the x's because there is addition and subtraction. Let me make that super clear. Just because I have a variable, a common factor on the top and bottom of a fraction, if there is anything being added or subtracted, I cannot get rid of it. Now, if my denominator, for example, okay, let's say my denominator was x minus 5 times x plus 2, I could cancel the entire x minus 5, but because that's a single factor itself, but I cannot just get rid of the x's. So please be very, very careful with that algebra. And again, if you have questions on that, or if it's something that you keep doing incorrectly, talk to me, let me help, okay? All right, so back to this. As it is, remember the original functions did not have domain restrictions, but now that this is in the denominator, it can't be equal to 0. So I'm going to solve x squared minus 1. I'm going to set this equal to 0 and figure out what can x not be. All right, now I can do this a couple of ways. I can factor it, x plus 1 times x minus 1, and get x equals 1 and negative 1. Or I could say that I'm going to, let me come up here. I could do x squared equals positive 1 because I added 1 to both sides. The thing about doing it this way is you need to be really careful and make sure that you put the plus or minus, or actually I don't need the radical because square root of 1 is 1. So when we take the square root, we're applying a square root that was not previously there. Square root of 1 is 1, but we do need the plus or minus there. So the domain is all real numbers such that x does not equal plus or minus 1 because those give us division by 0. Okay. Oh, look at that. We already did this. Okay. So all real numbers, all real numbers, all real numbers, and that. Bam. Got it. All right. Last ones here, and we'll do the domains as we go again. Okay. So we have two rational functions. These are called rational functions if we have a polynomial on top and bottom. So first I'm doing f plus g, up a little bit. So this is going to equal, whoops, 5x plus 1 over x squared minus 9. It's a little bit bigger. And then plus 4x minus 2 over x squared minus 9. How convenient is that? We already have a common denominator, so we don't have to get a common denominator. When we add fractions, if the denominators are the same, then we combine the like terms in the numerators. So I have 5x plus 4x, which is 9x, and then 1 plus negative 2 is negative 1, all over x squared, oops, don't need that, x squared minus 9. Now, if there was a common factor in the numerator and denominator, I would want to cancel that out. It would not change that I still have a domain restriction from the original functions, but it would simplify the way I write it. In this case, though, x squared minus 9, I know that to be x plus 3 times x minus 3, and neither x plus 3 times or x minus 3 can be divided into 9x minus 1, so I don't need to worry about reducing that. And then for my domain is all real numbers except anything that makes my denominator 0, which is negative 3 and 3, okay, because we just factored it there. So we're going to say all real numbers such that x does not equal plus or minus 3. Okay, if you've not already, I would suggest you pause it, try a couple of these and see if you get the same thing I do. All right, for part B, this is 5x plus 1 over x squared minus 9, and then I'm subtracting the entire quantity, 4x minus 2 over x squared minus 9. Again, common denominators already, so we combine the numerators, but we need to be careful and distribute this negative. We are subtracting that entire quantity. So 5x minus 4x is 1x, and then 1 minus negative 2 is a positive 3. And then we divide that by x squared minus 9. Okay, in this case, remember that this factors x plus 3 times x minus 3. In this case, I am going to reduce the x plus 3's and have just a 1 left in my numerator and just an x minus 3 in the denominator. So you do need to simplify if possible. Okay, now, because our original functions, we could not have x equal positive or negative 3, we still keep those same restrictions for the domain on the difference function. So it's still all real numbers such that x is not equal plus or minus 3, even though once reduced, it's okay to have a negative 3 in there because negative 3 minus 3 is not 0, okay? Again, this goes back to the restrictions from the original functions, okay? And if the original functions can't have an x value of 3 or negative 3, then we still can't in our difference. All right, so C, we are multiplying, come back up here. We are multiplying those functions, okay? So this is equal to 5x plus 1 over x squared minus 9 times 4x minus 2 over x squared minus 9. When we multiply fractions, we multiply the numerators together and denominators together. So I multiply my numerators, and I get 20x squared plus 4x minus 10x. So, whoops, minus 6x, and then minus 2, all over x squared minus 9 squared. Or if you want to write x squared minus 9 times x squared minus 9, you can. Or if you want to write that out as x to the 4th minus 18x squared plus 81, that's totally fine as well. I don't care. I would actually stop right here and leave it in the factored form. Remember, if it can be reduced, it needs to be reduced, like on the last one. So there's no point in multiplying it together if I'm just going to turn around and try and reduce it anyway. In this case, it doesn't reduce. I can't factor x squared minus 9 or x plus 3 or x minus 3 from that. Okay. So I'm actually just gonna stop right here. You do not have to expand it. It's not unsimplified to leave it like this. Okay, and then domain restriction, again, same as the previous one, all real numbers such that x does not equal positive or negative 3. Okay, then the last one for D, we're doing f divided by g. So this is going to be equal to 5x plus 1 over x squared minus 9, and then that whole thing is over 4x minus 2 over x squared minus 9. Now, we can look at this one of two ways. We can say, I know that if I'm dividing by a fraction, that's the same as multiplying by the reciprocal. So I could take this, flip it upside down, move it up here, and multiply by the reciprocal. Or another thing is, if we're getting rid of complex fractions, we look for the denominator of the inside fraction, which in this case is x squared minus 9. And we're just going to multiply the whole thing by that over itself. The reason we choose this, okay, is because it's going to cancel out the entire denominator there, and I'll have 5x plus 1 left, and then the entire denominator there, and I'll have 4x minus 2 left. Okay? Now, for our domain, we still cannot have positive or negative 3, even though there's no x squared minus 9 left in the resulting function. There is in the originals, okay? So still can't have plus or minus 3, but also we have a new value that we can't have. If 4x minus 2, if I set that equal to 0, I get x equals, so move the 2 over, or add the 2, divide by 4, we get 1/2. If x is equal to 1/2, that gives me a 0 in my new denominator, so I also cannot have, so x does not equal 1/2. And there's our resulting domain.